Alright, so what we're going to do in this section is we're going to look at a pretty important notation for functions called function notation, and we're going to incorporate that with linear modeling that we've been doing in chapter 2. Alright, so this right here is kind of a big deal. You know, when we have a function, we represent it with a mathematical notation, and we use this to indicate a function, and that's read as f of x, and we use that to represent y. So basically, instead of using y equals 2x plus 1, by using function notation, we could rewrite y equals 2x plus 1. We just replace the y with f of x, and we have f of x equals 2x plus 1. This is just function notation. It just replaces y. And we use it to represent, by doing this, we could represent an equation as a function. Here's a big warning right here. This does not mean f times x. Just think of it as this right here. We take our input for x, so we plug something into our function, and then we get an output for y. That's all it is. So, as like a little warm-up right here, let's look at this. Let's evaluate f of x at 5. Alright, so to do this, I'm just at 5 means x equals 5. So I'm just evaluating this function at 5, so I'm plugging 5 into my function. So wherever I see an x, I replace it with 5. So I'm going to have negative 4 times 5 plus 2. This is going to be negative 20 plus 2, which is negative 18. And that's it. That's the answer. So when you plug in 5 into this function, so think of it as that input. My input was 5, my output was negative 18. That's it. If we have more than one function, we could just use different letters to represent. We could just use different letters. So this letter right here, this letter right here, this letter right here, they're that's the name of the function. So they're all, that's the name of a function. That's the function name. That's just used to differentiate between multiple functions if you have them. So again, this is not f times x, this is just f of x. You're plugging in x to get y. Input, f of input equals output. That's how you want to think of it. So on page 2 I have multiple functions, right? Here's f of x, here's g of x, here's h of x. This is actually a polynomial function because it's squared. This is a rational function. This is a linear function. Don't worry about the fact that these are different functions. All you have to worry about in this section is getting used to evaluating functions at inputs and getting an output. That's all you have to do. So evaluate the following functions. So f at negative 2. So this means negative 2 is going to go into f of x. So this is f of x here, so wherever you see an x, you're going to place it with negative 2. Right? So this is 2 times the quantity, so x here is going to be negative 2, and that's to the second power, minus 3 times my input, which is negative 2. So how do you do this? Well, remember please excuse my dear Aunt Sally, your order of operations. So we do the exponents first, right? So this is going to be negative 2 to the second power, right? So parentheses negative 2 to the second power is 4. When we get to the section that deals with exponents, I'll show you that later, but this is going to be caret 2, right? So that's going to be 4. So this will be 2 times 4 And then minus 3 times minus 2 is positive 6. 2 times 4 is 8. Plus 6. 8 plus 6 is 14. So my input in this function was negative 2. My output was 14. Alright. And that's it. What about number 2? So g of 3. So the name of the function is g, the input is 3. So I'm plugging 3 into the g of x. That's this one. Okay. So plug in 3 here. You're going to get 4 times 3 minus 2 all over 5 times 3 minus 1. So 4 times 3 is 12 minus 2. 5 times 3 is 15 minus 1. 12 minus 2 is 10. 15 minus 1 is 14. 10 over 14 reduces to what? 5 over 7. You could use your calculator, but you could factor this to 2 times 5, 2 times 7. The 2's cancel out. You're left with 5 over 7. So my input in this function was 3. My output was 5/7. That's it. You know, I just want you to get, in this section, I just want you to get comfortable with evaluating functions. Your input, plug in, output. Now, sometimes that being said, sometimes your inputs aren't just numbers. Sometimes they're expressions or variables. Like this, we're going to plug A into H. So when you plug that in, you're just going to get, alright, my input is A. So wherever I see an X, I'm going to replace it with A. So I'm going to get 3 times A minus 5. I can't do anything with that. I can't, you know, add or subtract or anything. This is just an expression. So that's it. I'm done. I'm done there. That's it. Whenever you plug in something to a function, you're just evaluating it. There's nothing to evaluate here, so I'm done. I'm not solving for anything. I'm just evaluating. Again, here I'm plugging in the expression a minus 2 into h, which was 3x minus 5. So it's going to be 3 times my input. What's my input here? A minus 2. So it's going to be the quantity a minus 2 in replace of 5, or x, and then minus 5. All right. Now evaluate. All right. How do I evaluate here? Distribute the 3. That's all I can do. 3 times a is 3a. 3 times minus 2 is minus 6. Minus 5, I could combine the minus 6 minus 5 and get 3a minus 11. There's nothing else I could do, so that's it. Just because you get an algebraic expression doesn't mean it's wrong. You're not always going to get a number. I want you to recognize that. When you're evaluating functions at numbers, or at variables, or expressions of variables, sometimes you're going to get a number as the output, or you're going to get an expression as the output. It just depends what you have. Okay? Alright. So on page 3, if I have this function, evaluate it at 4. Alright, we've done that quite a few times. So just plug in 4 for x. So I'm going to get 3 halves times 4 minus 1. Well, 3 halves times 4, that's 4 times 3 is 12 over 2, which is 6. 6 minus 1 is 5. Easy enough. Now, number 2, I want you to think about this. Find x when f of x is equal to negative 4. Now here I'm not plugging in negative 4. What I'm doing here is I'm trying to find what my input is when my output is negative 4. So what I'm asking here is different to what I've been doing here and over here. Over here I'm asking what's my output when my input is this and that and so on. Here I'm asking the opposite. What's my input when my output is negative 4? Well, my output is negative 4, and that's my function's equal to, but I already know what my function is. So what I could do is I could set my function equal to the desired output, which is negative 4. And then from here I could just solve for x, which is what I'm trying to find. So how do I solve this for x? Add 1 to both sides. -4 plus 1 is -3. So now from here, to solve this for x, you can multiply by the reciprocal of 3/2, which is 2/3. The 2's cancel, the 3's cancel, you're left with x. On the left, 3 times 2/3, well, the 3's are going to cancel, so you're just going to be left with -2. So in this problem right here, when you're finding x, you want to set the function equal to the desired output and then solve for x. You're not, I'm going to say this, do not do this. That's a frown face. Don't do that. That's not what I'm doing here. Alright, do not do that. This is what you do. This is a very common mistake I see students do with these kind of problems. When you see the questions for this, they immediately do this. No. No, 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 no. Alright. So again, remember, so how do we evaluate functions when we have a graph? It's similar to when we have like a linear model or anything. It's just basically all you're doing is when you're finding a function at 4, you're just finding the value of y when x is 4. That's what this is saying, you know. Find y when my input is 4. It's the same thing. Remember, the first page of the notes says the following. F of x is equal to y. We're just using a specific notation, but they're both the same thing. We're just getting used to the idea of function notation here, which shows up a lot in mathematics. It shows up all the time. So, how do I find y when x is 4? Well, x is 4 is right here, right? So I go up to my line, there it is. What's my y coordinate at that point? Well, it's right here, it's 3. So find y when x is 4, well, it's right here. You could just go over to see that's 3, or it's already labeled as the order pair right there. So that's, or I could say the following. F of 4 is 3. Either this or this are the exact same thing, just written differently. This is what function notation, this means this. When you see this, that implies this. That's it. Question 2. When x is equal to 0. So what's y equal to when x is equal to 0? Well, when x is 0, that's right here. And at that point, my y coordinate is 1. That's it. That's the same thing as saying f at 0 is equal to 1. Alright, again, now question 3 and question 4. These are similar to this question. So now here I'm trying to find what x is when I know what y is equal to. So I'm looking at my y coordinate. -2. Oh, there's -2. Go over here. What's x? -6. And if I want to write that in function notation, I'm going to have f at, now what's my input here? It's not y, it's x. My input is what x was, which was -6, the value I found. And that's equal to my output, which is -2. Question 4, find x when y is equal to 0. So when the y coordinate is 0, so that's, when's y 0? Well, it's right here. Right, the y coordinate is 0 right here. It's at this point. I'm looking at where it's up and down. My line is right there at y equals 0, so the x coordinate there is -2. And using my function notation, my input was f at -2 equals 0. I just want you to get used to the idea of function notation and evaluating functions and how they relate to x and y values and their respected function notation, because that's important going forward in most math courses that you take. Getting used to function notation is extremely, extremely important. Alright. So now what we're going to do is we're going to implement function notation with what we've been talking about with linear models. So again, x is independent, y is dependent variable, and based upon that, using the function notation, I know this is light, so I'll just write it here. So here's our function name, right? This is f of x. The independent variable is the input, and the dependent variable is the output. And since this is our function notation, well, basically all we're doing here is we're representing the modeling that we've been doing, and now we're incorporating function notation with it. That's all we're doing. All right, so this data should look pretty familiar to you. We just looked at it in the previous section, didn't we? Actually, let me get those notes out. Hey, here's the notes from the previous section. Here's the data we looked at, isn't it? So, someone took that data that we looked at in the previous section, and they said a possible model for this data is right here. Now, when we did this ourselves, remember when we did it ourselves? This is the model we got by hand, which is good. This was the linear regression equation, which is the best, but someone said we're going to use this model. It doesn't, this is just another model, just like this one's another model and this one's the best model, but this is also another model for this data. All three of these can represent this data. This is the best one, but just for the purposes of this problem, we're using this model. Normally we would use the line of best fit, but just for the case of this problem, we're just saying, all right, we're going to use this one. That's all. We're just going to use this one. Now, using that model for this data, we're going to answer the following questions on the next page. Rewrite that equation with the function name g. So, okay, I want to rewrite this model with the function name g, Remember, this is the function name, the letter f of x, g of x, h of x, whatever. Now, remember how the data, let me back up a second. Remember we let P be the percentage of adults who smoke, T year since 1990. So when we did it in the previous section, this was 70, 80, and so on. This was the variable T, this was the variable P. Independent was T, dependent was P, right? So I want to rewrite this with the function name g. So I'm going to have g of my input equals my output. So I'll just copy that down up here just for reference. P equals negative 0.48 T plus 71. Right? Okay. So I want to rewrite that model with the function name g. So I'm going to have g of my input, which is T, equals my model. That's it. This is the function name. This is my input, and there's my output. Okay. Now question 2. Find g at 117. Interpret what this result means in this situation. So how do I do this? I'm plugging, this is my input into my function. So I'm plugging 117 in to my function. So I'm going to have g at 117 equals, so wherever you see a t, you replace it with 117. Negative 0.48 times 117 plus 71. So without your calculator, so negative 0.48 times 117 plus 71. So 14.84. Okay, so I want to interpret what this result means in this situation. So if I wanted to write this as an ordered pair, right, how would I write this as an ordered pair? This means that my input was 117, so that's my x value, well in this case t, and my y value is my output, which is 14.84. Right? Now, this is the independent value, this is the dependent value. What is independent? Independent is t. Alright? What does t represent? That's the year since 1900. So when I interpret this, this right here is the year since 1900. And this right here represents what? That's the p value. That's the dependent value. That's the percentage of people who, that's the percentage, right? This is the p value. That's the percentage of American adults who smoke. American adults who smoke. So to interpret this in a sentence, you're going to say, alright, so 117 is how many years since 1900? Well, 1900 plus 117 is 2017. So, interpret. In the year 2017, 14.84% of American adults smoke. And they just say smoke. It doesn't say anything about, it doesn't say smoking cigarettes or smoking cigars. It just says smoke. Alright, So question 3, find t when g of t equals 30. So here is, remember, don't do this. Don't do that. That's a no-no. Don't plug in 30 at G. I see that mistake all the time. Here you're going to set 30 equal to our 30 is the desired output. Well, my function is equal to this, so I'm going to set 30 equal to my function. So my function equals 30. Now you're just going to solve for t. So how do you do that? Subtract 71 from both sides. (30 minus 71 is negative 41. And now here you're going to divide both sides by negative 0.48. That'll get rid of that. So t equals negative 41 divided by negative 0.48 gives me 85.41. So I'm going to round that to, so that's approximately 85 point. Oh, okay, I'll keep it as 85.4. That's good. That's an approximate sign. This just means approximately. Alright, so write this as an ordered pair. Remember, t goes first. T comma p. T comma p. Again, this is the number of years since 1900. This is the percentage of American adults who smoke. So when you interpret it, you're going to say what? 85 years since 1900 is the year 1985. So in the year 1985, 30% of American adults smoke. That's it. I cannot stress this enough. Don't do that. If you do this, then you're not quite understanding function notation, in my opinion. You have to know the difference between setting it equal to a desired output and evaluating at an input. You have to understand the difference between these two. I see these get switched around in students' minds all the time. But if you do the homework and practice the concepts, it actually starts to stick. Okay. Find the p-intercept of this model. Interpret what this means in this situation. So the p-intercept, so again, the p-intercept is the value of p when the other variable is equal to 0. Alright? What is p when t equals 0? Alright, so that's easy. Well, t is equal to 0 means that's my input, isn't it? So I'm just evaluating. So what this means is I'm going to evaluate my function at 0 because t is my input. So when I plug in 0 to my function, that's easy. Plug in 0. So I'm going to get negative 0.48 times 0 plus 71. Well, 0 times this, that goes away. So I'm just left with 71. So my ordered pair here is, well, it's the intercept. So my ordered pair here is 0, comma, 71. That's the p-intercept. That's where it crosses the dependent axis. Interpret it. again, same thing. This is the number of years since 1900. This is the percentage of American adults who smoke. So 0 years since the year 1900 is what year? 1900. So in the year 1900, 71% American adults smoke. Now, even though I don't ask you here, I want you to think about this. Is this model breakdown? Is this model breakdown? Yes or no? And why? So, first of all, remember, model breakdown occurs in two places. The result makes no sense whatsoever, or it's too far away from our given data that we can't make a conclusion. So, why don't we look at our data? So, our data starts in the year 1970, right? And it ends in the year 2010. This result we got is the year 1900. Now, for this data, 1900 is a little too far away from the starting year 1970. So in other words, this result is too far away from our starting point that the result may or may not be accurate. So yes, this is model breakdown. Why? Because the year 1900 is too early compared to our starting data point. Our starting data point was the year 1970, but 1900 was too early compared to that, so the confidence of this result is limited. That's why it's model breakdown. You know, both of these results are somewhat possible, but you know, 1985 is smack in the middle of this data, so this is okay. This is good. 2017 isn't too far away from 2010. It's only 7 years away. 1970 is 70 years after 1900. So these two results are okay. These two results are fine. This one is a little too far away in the present. It's too far. It's too early. Now let's look at the last question for this. So this is the last question for that problem. So find the t-intercept. Now remember, the t-intercept is the value of t. This is saying what is t when the other variable, which is p, equals 0. So, okay. So p equals 0, that's the dependent variable. That's what my function's equal to. So what I'm going to do is I'm going to set my function equal to 0. My function, I'm going to set this equal to 0, right? Because that's what p is. P is 0 in this case. So I'm setting this equal to 0 and solving for t. So negative 0.48 t plus 71 equals 0. Now solve for t. Subtract 71. Divide by negative 0.48 t, or negative 0.48, I mean, sorry. So t equals negative 71, so calculator time. Negative 71 divided by negative 0.48 gives us 147.9 approximately. right? So I mean, I could round that up to 148, right? And the reason being is this. Remember, this is the number of years, so it's close enough to 148. I'll just round it up to that. So this is the order pair, 148, comma 0. Interpret that. So what does this mean? Again, this is the number of years since 1900, and this is the percentage of Americans who smoke. So 148 years since 1900 plus 148 is the year 2048. So that's in the future. In the year 2048, 0% of American adults smoke. Is this model breakdown? Yes or no, and why? Well, this is model breakdown, definitely. It's model breakdown for two reasons, actually. The year 2048 is a little too far in the future from 2010. Also, it could be model breakdown because this says in the future 0% of American adults smoke. Well, I'm sure there's going to be at least a few people in the future that smoke cigarettes. So this is actually, or well, smokes in general, right? Not specifically cigarettes, but you get the idea. This is model breakdown for two reasons. Yeah, for two reasons. You know, because some people in the future will smoke, and also because this result itself is just so far away. But more specifically, there's at least a few people in the future that will smoke. So yeah, this is model breakdown. So, you know, hopefully when we do modeling now, when you find a model, instead of writing it as an equation, just replace the p with the function name of the input, which is t, which is what we did here. And then just get used to evaluating functions at values and setting them equal to values and solving for the independent variable. Don't do this in this situation. So the last thing in this section is finding the domain and range of a model. So if you remember, from the last section in chapter 1 when we did domain and range, the domain is the set of all values the independent variable could take. The range is the set of values your dependent variable could take. Okay, so in this example, a store is open from 9 a.m. to 5 p.m. Mondays through Saturdays. Let the function be equal to I. So, alright, let me write down independent and dependent. I is going to be an employee's weekly income in dollars, and T is how many hours at $10 per hour. Alright. Technically, I could have cut this off right here. This is just extra information. So my dependent variable is income, right? That's what I is income. Your income depends on how much you work, right? The more hours you work, the more you're going to make. Your income depends on how long you work. If you have a job and you're paid hourly, then you know exactly what I'm talking about. So I want to find an equation for the model F. Alright, so we're making a linear model. So my function is going to take this form, mt plus b. I don't use x here because I'm using t instead. mx plus b. Right? I'm just putting this here for reference just so you could see the comparison. So once I find what my slope and y-intercept is, I'll have my equation for my model. Okay. So my function measures how much money I'm going to make. So how do you calculate your weekly paycheck? You multiply the number of hours you work. So the number of hours you work here is T, right? T is the number of hours you work each week. You multiply the number of hours you work each week by how much you make per hour. Right? How much do they make? $10 per hour. So to find out how much you make in a week, which is what the function measures, that's going to be equal to how much you make per hour, which is 10, times how many hours you work each week, which is T. Now, the plus B part doesn't show up here because I don't, like the plus B part would be like a bonus or something, like with a $50 bonus or something. Well, that doesn't show up here. So this is my model. That's it. That's how much you make working T hours, right? So if you work 30 hours, well, 30 times 10 is 300. You've made $300. Now we're not factoring in taxes or anything here or overtime. We're just looking at straight hours times your rate. That's it. Okay, so now let's find the domain and range here. So the domain is the set of all values for t, right? And the range is the set of all values for my dependent variable, which is I. So how many hours can I work according to this problem in a given week? So how many possible hours are there? Well, the store is open from 9 a.m. to 5 p.m. So that's 10, 11, 12, 1, 2, 3, 4, 5. So that's 8 hours each day, right? Mondays through Saturdays. So that's 6 days, right? Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So 8 hours a day times 6 days. What's 8 times 6? 48. So T can be anywhere from 0 hours to 48 hours. How do I write that as an inequality? Because I could work 0 hours, I won't get paid, but I could work a whole week, 48 hours. Now I'm not factoring in overtime here. So remember, and we're going to talk about inequalities later in chapter 3, but this means the value of t gets caught between and including 0 and 48. So that's the domain. This right here describes that. That's the domain. T could be greater than or equal to 0, but it could also be less than or equal to 48. So this means I could work 0 hours, I could work 48 hours, or I can work any hours in between. So if I make, if I work 0 hours, so what's my I represents the income, right? So if I work 0 hours, so this is going to be anywhere from something dollars to something dollars, right? If I just fill in the blank here. So my income, right? So if I work $0, or I'm sorry, I already said it. If I work 0 hours, how much money am I going to make? $0, right? You don't work, you don't get paid. Or I could just plug that in here, right? 10 times 0 is 0. So I can make anywhere from $0 to, now if I work a full week, 48. Plug that in here. 10 times 48 is $480. So my income can range anywhere from 0 to 480. And that's my range. So, you know, we'll talk more about inequalities in chapter 3, but yeah, that's the domain and range of a model. And that's important because you want to be able to distinguish what my possible inputs and outputs are for a particular equation or a particular function. That's important to understand. So, yeah. So, yeah, from this section, the big thing you should take away from it is evaluating functions, knowing the difference between evaluating a function and setting a function equal to find the input, and, you know, finding the intercepts, doing interpretations of those results, and finding the domain. So, you know, the last section in 2.4, we're going to actually, you know, we're going to look at a closer inspection of the slope. We're going to look at the slope a little bit more in 2.4, but and that'll close out chapter 2. So, yeah, so that's function notation, which is very important. It's absolutely important. You're going to see it from here on out. You're going to see it a lot. It's going to show up in just about every chapter we look at from here on out, and for most math classes you take. So that's it for this section, and that's the end of this video.